that results from human activities, where there's an increased rate of instances of energy released, or seismicity, beyond historical or normal levels. You know, there are literally thousands of earthquakes that happen on a daily basis around the globe, but only a very small percentage of them are actually felt. Some of the activities that can potentially cause earthquakes would be development of geothermal reservoirs, mining, damming impoundments, where if you create a dam, you suddenly put a lot of weight on the world where there wasn't any before, which changes the stress fields. And that can actually cause rather large earthquakes on the order of 6 or 7 on the Richter scale or the magnitude moment scale. And so that would obviously be a pretty major earthquake. Oil and gas operations, there has been some, like I said, relatively isolated, but yet documented cases where oil and gas developments caused some earthquakes, mostly with conventional reservoirs. And then, the underground injection of fluids for waste disposal, whether it's oil or gas wastes or other industrial wastes that are disposed of via underground injection wells. There's 2 main types of induced seismicity. There would be that caused by shear stresses and that caused by tensile stresses. The shear stresses, that results in the larger earthquakes, the ones we feel here. Generally, we don't feel earthquakes that are, roughly 3 or less on the scale. Above that, we start to, probably feel them. Tensile stress can cause induced seismicity, but that's the kind of seismic activity associated with, say, hydraulic fracturing. There's a tensile stress imparted, and it's actually kind of a coupling between tensile and shear stresses. But again, these are very low on the scale of earthquakes, and so generally you're looking at something less than 1, sometimes less than 0, like -1 on say the Richter scale or the moment of magnitude scale, which is more commonly used nowadays. So just to give a sense of the magnitude. Really, the magnitude of an earthquake is going to hinge on how much slip occurs along the fault, how much stress there was in the fault before the slippage occurred. So that translates into just how fast the failure is and how large of an area over which that slip occurred. The seismic moment is what basically the variable that allows us to measure the magnitude of an earthquake. And so it's a factor of the slip and the area that's slipped, along with the rigidity of the rock. If you have a relatively soft rock, that kind of absorbs more of the energy. If you've got a more rigid rock, say a crystalline bedrock, that's going to tend to create more of a widespread impact. So another factor is the depth at which the epicenter of the earthquake occurs. The larger earthquakes are more deeply seated in the earth because there is enough energy at those depths to create lots of slip over large surface areas. Whereas as you get closer to the Earth's surface, there's not as much energy stored or potential energy stored, so the rocks aren't under as much critical stress. And so there's not as much potential for causing larger magnitude earthquakes. And so, again, the seismicity associated with hydraulic fracturing, you're looking at magnitudes that are typically less than 1, almost always less than, or typically less than -1, and almost always less than 1, except for a couple of instances. But the scale on the left there just gives you a sense of some of the energy equivalents of some of the earthquakes out there. And so, Chile obviously had a major earthquake in 1960. Alaska, these are devastating earthquakes if they're over, depending on, again, some of the factors, including the rigidity of the rock. But, anything over really 6 is quite a significant earthquake, and it's something you'll see on CNN in the news. You know, when the atomic bomb was dropped, that was equivalent of about a 6 on the magnitude scale. But again, you know, a bolt of lightning striking the Earth is about 2.5 on the magnitude scale. So just to give you a sense, it's kind of a nice chart to just help you understand the relativity of it all. As I'd mentioned, you know, it's shear stress that causes most of the larger earthquakes. And so, in essence, if you have, you know, say a fault, and that fault is under critical stress, but the faces of the fault are, the friction there is great enough that it doesn't allow the slip, then, you know, that fault will just remain at maybe a near critical stress. But it's when you inject fluids down into that fault, you begin to change the pore pressures, and in essence, you lubricate that fault surface, and that's what allows slippage to occur, and that's what translates into an earthquake. And so therein lies really the potential for hydraulic fracturing or the disposal of waste fluids down into the earth to be the origin or the cause of induced seismicity. It's the injection of fluids, in essence changing the pore pressures and you know, changing the stress field dynamics down there. And so this would be just a schematic that shows you know, a horizontal well in a shale where there's existing fractures in the shale, both before and after drilling. And so when you're hydraulically fracturing a shale, you're trying to, you know, take existing fractures and make them move apart from one another. And so that would be the tensile stress. And so again, the seismicity associated with that is typically quite low, nothing that we would ever feel here on the ground surface. I've heard some who are in the business of measuring the seismicity or the microseismicity associated with hydraulic fracturing say it's the energy equivalent of taking a gallon of milk, holding it about, you know, shoulder high and dropping it on the ground. That's the amount of energy that's being released from the hydraulic fracturing process. And so if you can imagine then that gallon of milk's energy propagating up through, you know, a kilometer or more of the earth, you know, really not going to happen. But what the, you know, again, there is a whole field of microseismology that's monitoring the hydraulic fracturing operations of these fields. And the idea is that they can actually have sensors either at the ground surface or nearby wells that are sensitive enough to be able to pick up on that seismic pulse from hydraulic fracturing. And what that allows is them to be able to sort of zoom in on where the extent of the fracturing, or how extensive the fracturing was. How far up did the fractures grow from the well? And so that's, you know, pretty amazing that this technology is out there. You know, and the data is fed into sophisticated computer models, but it allows the companies that are conducting the hydraulic fracturing to figure out, you know, how far out are our fractures going? Did they go out as far as we intended them to? And allows them to more or less optimize the fracturing process. So this is a graphic I took from the U.S. Department of Energy that shows a series of oil wells, as denoted by these black lines, that are drilled down in. And then there are secondary or enhanced oil recovery wells, as shown with these blue lines. And the idea is that you can inject fluids, water, typically brines from other wells, back down into these enhanced oil recovery wells, and in essence sort of push the hydrocarbons over to the oil and or gas wells, and therefore get more oil, in this case, out of the ground. And there have been some induced seismic events associated with these injection wells, because what you tend to do is inject fluids over longer periods of time, and then those fluids can migrate out, and if they were to encounter a fracture under critical stress, you can have that induced seismic event. This shows a map of the different kinds of induced seismicity that have been documented in the U.S. And again, this is from the National Academy of Sciences. They recently put out a publication. You can see there's a few different activities that have caused it, whether it's oil and gas extraction. This is mostly out in California, or it's the secondary recovery operations that I just described. A lot of that's going on in Texas and down in the southern states. Wastewater injection of the produced fluids via the disposal wells. There was a fairly well-publicized event up in Youngstown, Ohio on New Year's Eve of 2011, so just a little over 11 months ago, that registered about 4.0 on the earthquake magnitude of moment scale. Geothermal, again, mostly up in Northern California, Nevada, and then hydraulic fracturing. There was one instance here recorded in Oklahoma, just to give you a sense of how rare it is to have any sort of induced seismicity that's significant enough to be able to felt at the ground surface. This is also taken from the National Academy of Sciences, and it talks about the number of events as compared to the number of projects out there, just to give you a sense of how rare some of these episodes are. And so there's, again, with geothermal energy development, it's actually kind of common to have some sort of induced seismicity. They're injecting fluids down there, and so again, that changes the stress fields down there. With oil and gas recovery here, you can see with withdrawal, there's about 6,000 different fields, and there's been about 20 sites, mostly out in the Midwestern part of the U.S. or the western part of the U.S., and only 5 of these have actually been felt, so they were 4 on the moment of magnitude scale. Again, with secondary recovery operations, 3 episodes out of roughly 108,000 wells. Just to, again, give you a sense of these aren't common events, but they can occur. Hydraulic fracturing, 1 event that was in Oklahoma, and that's out of roughly the 35,000 wells, shale energy wells that have been drilled in the U.S. And with wastewater disposal, basically a higher frequency of these incidents, and mostly have been in Arkansas, Colorado, or Ohio. And we'll talk about a couple of these specifics as case studies. Again, I touched on microseismic monitoring, really a pretty fascinating technology that really is useful in so many different ways. In one, it allows the companies to be able to figure out just how far out their fractures go, and allows them to really, more or less optimize their operations. It tells us how far the fractures are going, and are we, creating fractures that are growing up too far, and is there, a risk of contaminating groundwater from hydraulic fracturing, which has really been the major question that's been asked out there. So we're saying, can fractures that are being induced at, we'll say, 1 to 2 kilometers below, maybe even 3 kilometers below the ground surface, can those fractures propagate all the way up to near the ground surface and impact groundwater? The simple answer on that is that's extremely highly unlikely. As a geologist, I don't say that anything's impossible, but that kind of a scenario is not proven out to date, and so it's a highly improbable possibility. And this just gives an example from a well in the Barnett Shale, which is really the most mature of the shale plays in the U.S. And so they're operating at depths of roughly 2,000, 2,500 meters or so. And basically, what these blue dots represent are the sort of vertical extent of the fractures that were induced from hydraulic fracturing. And so you can see that the fractures tend to grow up, on the order of maybe 100 meters or so upward, and actually maybe 200 meters or so, or maybe a little less than that, downward. And a lot of that has to do with the particular stress field, is whether the fractures are going up or down or out. And so really having a good geological understanding of that stress field is critical, because you want your fractures to grow out. And if you're drilling your wells and trying to induce fractures in a way that the stress field won't really allow, you're not going to be very successful in this. And so it's really critical to understand which way those fractures are going to grow out. This is an example of the fracture length associated with Marcellus Shale wells as mapped out by microseismic surveys. And so here, again, we're operating at somewhere between roughly 2,000 to 3,000 kilometers. This red line would represent the depth of the wells, and then the blue lines would represent the vertical growth of those fractures upward from these wells, or downward. You'll note that there's very little downward growth with these fractures. Most of the growth is upward. One of the reasons for that in the Marcellus in particular is that there's what we call a frac barrier below the Marcellus, which is in essence a limestone layer that's under a higher compressive stress, compressive strength, if you will. And so the fractures can't penetrate down through it very effectively. And so it's much easier for the fractures to grow up than down. And so that's why we see that upward growth as compared to downward growth. This maps out where the bottom of the aquifers are, the depth to fresh groundwater, which in most cases is going to be somewhere between 100 to maybe upwards of 300 meters below the ground surface. And so the idea is that you're always going to be approximately 1.5 or 2 kilometers or more below the fresh groundwater zone with these fractures. And so there's really, to date, no fractures have grown way out of the Marcellus zone and impacted groundwater. And that's really the case for all of the shale plays in the U.S. from all of the data that's out there to date. There's really no known cases of groundwater contamination from the hydraulic fracturing episode or portion of the process itself. Again, I'd mentioned that there's frac barriers, basically layers, often limestone, that are under such compressive stress that fractures can't grow through them. So you have to consider that there's only a finite amount of energy that's being put down into the shale. And so the fractures can only have so much potential for growth. And once they hit a layer that's much harder, if you will, it impedes the growth and it stops. And so in the Marcellus, there's a limestone layer below it, the Onondaga Formation. And then we've got a limestone layer about roughly 1,000 or so feet above it, known as the Tully limestone. And so if a fracture were to begin to grow out of zone for some unforeseen reason, maybe it's growing along a pre-existing fault, that limestone layer would in essence stop the growth of that fracture. So there's really no potential for it to grow beyond that. This is a study one of my colleagues, Richard Davies, at Durham University in the UK put out earlier this year. And he looked at all of the various shale plays in the US and took the microseismic data out there and looked at what is the probability of fractures growing up to near the ground surface based on all the information we have out there to date. And so you have the depth of the wells and the fractures on the Y column. And then, so in essence, you've got the different major shale plays in the U.S., the Eagleford, the Woodford, Barnett, Marcellus, Niobrara. And then he mapped out the vertical growth of the fractures based on all that information that's out there in the public realm. And really saw that, again, pretty consistent with what we've seen is that, generally the fractures, say in the Marcellus or any of these other shale plays, really grow up maybe 100 meters, maybe 200 meters, but rarely 300 meters or more. That would be an outlier in the data sets. And so then he sort of cooked it all up into some probability charts here. And really the take-home story is here that when you look at how high up the fractures grow or how far down the fractures grow, most of the fracture growth is in that 100 to 200 meter zone, and then it dies off very rapidly. So, you have had fractures that have gone up as much as 500 meters, but that's an extreme case. Again, looked at the probability of fractures growing beyond a certain height, and again, once you get beyond 300 meters, most shale plays, the fractures just, there's no possibility. There's not enough pressure and force down there to make the fractures grow beyond that. And in one case, in a Marcellus well, it may have gone as far as 500 meters, but again, a pretty rare event. And still, when you're drilling at 2,000 meters or 3,000 meters, you still got a lot of rock in between that's been unfractured and it isn't being impacted. To look at the one case in the UK where they had the unfortunate incident of drilling their first shale well, fracturing that shale well, and inducing seismicity associated with it. So that's kind of the wrong step to start with here. But it was a pretty well-documented case. Occurred in spring of 2011. And company Quadrilla Resources was drilling in the Bowland Basin. And this is all actually out there in the public realm as far as this study. They looked at what caused this microseismic events. So in essence, they had two detectable earthquakes. Might have been felt at the ground surface at about magnitudes of 1.5 and 2.3. And then they had a total of about 50 little microseismic episodes. So 48 of them, too small to be felt. 2 of them big enough to maybe be felt at the ground surface. And so basically what you're looking at here is the rate at which they're injecting the fluids here in red. So they're injecting fluids at about 50 barrels per minute. So that would be roughly, let me see, 160, roughly 1,000 liters per minute in one of these wells, if I'm doing my conversions correctly here. Or actually probably 2,000 liters per minute, I'm sorry. And basically you've got the pressure they're inducing down there is on the order of 8,500 to 9,000 psi. So this is their injection phase. So this is what they're monitoring as they're injecting the fluids down into the shale. And this lines up with the time frame of injection. About 6 hours after the injection, they noticed the 1.5 magnitude earthquake, and then sometime later they noticed they recorded the 2.3 magnitude earthquake, and so they stopped. They started to look at all of this and said, "Yeah, we probably caused a small earthquake as a result of our fracturing operations." This is a seismic section from that same area that shows actually this would be the well that they drilled that had the induced seismic episode. Again, this is the first well that they drilled and fractured in a shale formation in the UK. And I should mention, so this is a two-dimensional seismic cross-section, which is really an important aspect of any kind of energy development, is to understand the geology. And by, in essence, doing a sort of a wide, large-scale seismic survey, you can figure out the depth to the shale that you're interested or other formation that you're interested in. You can figure out approximately the thickness of that. And then you can also figure out the geologic complexity of the formation. Are there folds in there? Are there faults in there? Are there particular features that you would rather not drill into because of the potential for maybe one, losing your well due to drilling complications, or two, causing some undesired seismic events? And so they took a look at the seismic data and realized that this was kind of a retrospective look, I believe, and realized that, yeah, indeed there are some faults in here, and the fluids that were being injected into the shale must have migrated into these faults that were, again, under some near critical stress, caused some slippage, translates into an earthquake. They also looked at the well itself. After there was the induced seismic events, they ran some tools down the well to see if it affected the integrity of the well. And in fact, it looked like the casing may have actually been deformed at a depth of about 87 feet. So they run what they call a caliper down the well that measures the diameter of the well. So they know what the well's diameter should have been in the first place when they installed this steel pipe down there. And then after they had the seismic issue, they reran that tool down the well and found that there must have been some slippage because the casing diameter's been altered as a result of some slip. And so there's actually what you might call sort of a pinch point down here between 8,500 and 8,600 feet where the casing was actually measurably deformed as a result. Due to all of the studies and events that took place here with this quadrilla well, they're currently going through the process of determining how to proceed forward, whether to proceed forward. It does appear that they will go forward with some drilling in the UK, but with what they're going to call a green, yellow, red light system, and basically record microseismicity as they're doing any hydraulic fracturing. If they don't have any, in essence, if they don't have any elevated or recordable microseismicity, then they'll continue with the drilling. If they have events that are between 0 and 0.5 on the magnitude scale, they would basically inject less fluids to see how it reacts. And if that seismicity increased to greater than 5, that would be a shutdown mode, and let's assess the situation and determine what's really going on here. So a fairly well thought out, conservative approach to seeing whether drilling and fracturing operations in this particular shale formation in the UK could have further seismic implications. I want to switch gears away from hydraulic fracturing and its seismic potential to underground injection wells. We touched on the fact that there have been a handful of noted greater than 4 magnitude earthquakes as a result of wastewater injection. And this is just a map that shows how many oil and gas injection wells we have in the U.S. We have about 151,000 of these wells. About 20% of them, roughly 35 or 40,000 of them, are actually classified for disposal. The other 80% of these are for enhanced oil recovery operations. So they're still injecting fluids down there, but it's not for waste disposal purposes. It's for oil recovery purposes. And this just shows sort of a nice schematic on what a typical injection well would look like. Ultimately, you've got a vertical well down into a sufficiently deep, sufficiently permeable reservoir that can accept these injected waste fluids. Other case study I want to focus on here is again, the Ohio episode that occurred on New Year's Eve last year. Everybody thought it was just like a really big party and everybody was jumping up and down at midnight, but in fact, it was an injection well that was obviously having some issues. And so they had actually had a series of seismic events and it took a little while to zero in on the fact that it was related to underground injection of wastes. But they had 12 low magnitude events during 2011 from about March to December of 2011. And the magnitude of those events ranged from about 2.1 to 4.0 magnitude earthquakes. And this is an area that you have the occasional earthquake, and so it's not unheard of to have an earthquake. It's, again, whether it's above and beyond the normal range or frequency of earthquakes, it really kind of makes it induced man-made. There were basically the well was drilled and they started injecting, and then about 3 months later realized, hey, we have some seismic events. In the spring of 2011, it began operation in December 2010. The seismic events, sort of the epicenters of these were all clustered together. So, the geologists and the seismologists figured, well, there must be some common thread here, some common reason. And they went down and did some testing on these injection wells. And, they did see that on the well logs there was enhanced permeability in these wells. Just at the interface where you've got the sedimentary rock sitting on top of the crystalline basement rock. And really, the sort of the root cause of these induced seismic events is that you've got deep-seated faults in the basement rock that are under, again, pretty critical stress because they're pretty deep, but they've never really seen much, if any, in the way of fluids before because they're so deep. And now you're allowing these fluids to inject down there, and again, you get the slip along that fault face, that fault plane, which causes the seismic event. And so, based on the location of the North Star well and the location of the epicenters, they began to put together the fact that all these epicenters were about 2,500 feet, or roughly 800 meters away from the injection well, and about 4,000 feet. So a little over 1,000 meters laterally from the well, and at about 800 or so feet below the wellbore itself. So it became sort of the focus point of the investigation. This is a map that shows all of the injection wells in Ohio. If you recall earlier, I mentioned there is currently 179 operating injection wells in Ohio. There's been a significant increase in the use of these injection wells for produced fluids disposal, largely as a result of the Marcellus operations in neighboring states. This shows the location of the North Star well at a depth of roughly 3,000 meters below the ground surface. So as a result of the seismic events associated with this disposal well, the Ohio Department of Natural Resources, who manages the underground injection control program, came up with a set of recommendations, which they're in the process of implementing. But basically what they're saying is, to avoid having future induced seismic events, they're going to do a thorough review of all of the known faults in the state, avoid locating any future wells near these deep-seated faults so as to minimize potential for any seismic events. On future wells that are going to be drilled, they're going to have to run a host of geophysical logs to make sure that these wells are appropriate for underground injection. They want to make sure that the pressures at which they're injecting the fluids into the ground are appropriate for the geologic conditions. Actually, these wells aren't capped at a certain volume of fluids that can be injected into them every day. They're capped at the fluid injection pressure. So that's what really sort of governs how much fluid you can inject into any of these wells on any given day. They would require having continuous pressure monitoring, And basically, all that data would feed back into the regulator so that they can make sure that these wells are being operated. Because what you wouldn't want to have is somebody inject fluids at a pressure that's higher than appropriate, because that's where you could, again, change the stress fields down there and cause seismic events. So just some final conclusions here. Hydraulic fracturing creates permeability, but it rarely creates unwanted induced seismicity, especially that's significant enough to be detected at the land surface. So that's a pretty rare event. There have been underground injection disposal wells that have caused some seismicity, generally, with a magnitude 4 or less, so you're not going to cause significant damage, but, certainly could be felt. And, obviously not every place is appropriate for disposal of waste fluids, and so we need to make sure that, there's adequate geologic characterization, we understand the stress fields down there, and what appropriate injection pressures could be applied to, for one, safely dispose of the waste while not causing, any ground shaking episodes. And finally, you need to make sure that you've got, the proper regulations. Ohio is, in the process of significantly upgrading their regulatory program, and so that might be a good model for other states or regions around the world as they go forward with this practice if it is used. So with that, I thank you very much and hope you all enjoy your lunch.